So in this video, I'm going to be introducing the idea of an integral and really how to implement it and some of the key properties behind it. And we'll also go over some practice problems. So as you can see here, I got pretty fancy. I wrote out all of this stuff ahead of time because I didn't want to make the video too long. And, before we dive into some practice problems, I'm obviously going to elaborate on what I've written here. So, an integral is essentially the area under a curve. A couple videos ago, or during my past couple of videos, that's what we've been concerned about. Remember, we worked with rectangles, just a bunch of rectangles or something like that, and then we moved on to just remember we basically we did delta x times f of x, all that stuff, and then we did a Riemann sum, and then we did a limit of the Riemann sum, and then basically what happened here, and then this basically we found out that this is the same thing as an integral. So you see here, we started with rectangles and we were able to just add together all those areas of some rectangles, and that was our approximation. Then we said, hey, what if we just condense this into a sigma, right? Um, and we basically just say, hey, the area is just the sum, sigma, of all of these rectangles. And then they said, well, we can get an even better approximation. In fact, we can get the exact area by taking the limit as n approaches infinity of f of x times delta x. Basically, we break up the area under the curve into infinitely many rectangles and add their areas together. In other words, the limit of the Riemann sum. And then we discovered that, hey, the limit of the Riemann sum, that's an integral, right? That's an integral from a to b, f of x dx, where dx simply means with respect to x. You can also say differential x. So, enough of that. That's really besides the point for this video. Just kind of showing about where all of this came from. We started with rectangles and then we built better approximations until we did the limit of the Riemann sum. And then, the limit of the Riemann sum was awful. Remember my last video? Like, holy crap, that was a mess. Basically just one video for like just one problem. That was terrible. We don't want to do that anymore though. So now I'm going to teach you these shortcuts. So again, just to reiterate, an integral is essentially the area under a curve. That's really what you have to know. And there's two types of integrals. The first one is the indefinite integral. So you see this, this is the integral symbol or the summa symbol. And you're going to see a function here, and dx means it's with respect to x. If I was dealing with, f of t, then this would be dt because we're integrating with respect to t. So the indefinite integral basically means that, hey, there's no upper and lower limits of integration. It means this doesn't run between an interval. It doesn't run over a to b. And, this will make more sense in a little bit. Like remember like when we were taking like integrals and stuff, we wanted the area between this point and this point. Well, that would be a definite integral, which is this guy on the right hand side. That's basically saying, you know, it's the area under the curve over this over this integral from a to b. That's what a definite integral is. An indefinite integral is it really just produces a general formula of what the area under the curve could be given some values of x. Um, it's basically like, with derivatives, we would take derivatives and we get some generic formula that would produce the slope of the tangent line if we were given an x value. The same thing here. So, but what you really have to know is that an indefinite integral, you're not going to see any values on here. It's just going to be by itself. A definite integral, you're going to have some values from a to b. That's all there is. So now we have some properties of integrals. And these are very similar to properties of derivatives. So let's look at these. So basically, number one states that if you have a constant out front of your function, let's say I had, 2x squared dx, then I can just bring that 2 out front. That's all it really means. So, sorry about that. That's the worst integral symbol I've ever seen in my life. So, basically means just the constant can move out front of the integral like I did here, where c is some constant, I can just kick him out front and the function stays within the integral. That's all it means. The next one states that integrals can move between addition and subtraction. That's parts 2 and 3, meaning that, if I had x squared minus x dx, that's the same thing as the integral of x squared dx minus the integral of x dx. Same thing if this was a plus, I'll just say plus up here, plus or minus. So same thing as if it was addition or subtraction. So like derivatives, integrals can also move between addition and subtraction. And those are really the three main rules for integrals, believe it or not. The tricky part here, and this might be a good news for you if you don't, if you hate remembering formulas, but bad news because there really is no official technique for integrating, products or quotients. There is no quotient rule, there is no product rule, there is no chain rule. There's just the figure it out rule. And there's a bunch of different integration techniques you'll learn later on in calculus. Such as use substitution, trigonometric substitution, partial fraction, blah, blah, blah. Don't worry about that. You really only have to worry about these right now. So these are really the main rules. And again, it's good if you don't like remembering formulas. You only have to remember three things, right? And these are pretty common sense already. Bad news is that when you encounter those, products or quotients, you have to be really clever about solving them. So I also have some bonus properties, and these are really if you're dealing with definite integrals. And one more thing I want to point out up here is that these could have also been definite integrals. I could have had a to b up here, a to b, all over the place. It doesn't matter. These mean the same thing for definite or indefinite integrals. So it doesn't matter. I noticed that for here I didn't put a to b, and I don't want you thinking that this is only for indefinite ones where there are no limits of integration. That's not true. This is the same for indefinite and definite integrals. So whether or not, it has these limits of integration, it doesn't matter. I just happen to write these as indefinite integrals, that's all. So here's some bonus properties though, and these only apply to definite integrals. So number one of the bonus properties states that, hey, if I have an integral running from one number, the integral running between two of the same number, like let's say I had integral running from 2 to 2 of x squared, then that's just going to be 0. So this means that if your upper and lower limits of integration are the same, it's just going to be equal to 0. So that's really just one other bonus property to remember. The next one is that if the lower limit of integration is bigger than the upper one, example, 2 to 1 x squared dx, then you can flip those limits of integration. You can just flip them around, and then you toss a negative out front of your integral. So this becomes 1, 2, x squared dx. That's all there is to it. So again, if the bottom one is bigger than the upper one, or the top one, then you can change the order like I did here, and then you toss a negative out front. That's all there is to know. So that's enough of the properties. Let's now do some examples. And I have several examples, and I'll try to make this as short as I possibly can. Okay, so let's say I was given, and this is a very general example. So let's say I was asked to compute this. The integral from 1 to 4 of, let's say 3 f of x minus g of x with respect to x dx. But then it also gives me this. It says the integral from 1 to 4 of f of x dx equals 2. And then it's also giving me that the integral of 1 to 4 of g of x dx equals 10. So what I first want to do here is I want to break this up into two separate integrals. So I'll do that. So I'll say 1 to 4, 3 f of x dx. Remember, this is just using this property up here. So this is second property, or this third property, and I can break it up between addition or subtraction. In this case, just subtraction. So the integral of 3 f of x minus the integral. Remember, the limits of integration stay the same here. So g of x dx. Okay, and remember the first property, if I have a constant, I can simply just bring it out front. So in the first one, I'm just going to bring this constant 3 out to the front. So I'm going to get 3, 1 to 4 f of x dx minus 1 to 4 g of x dx. So now let's look at this. Well, you can see here that, hey, what is the integral fx dx? What is this? Well, this is just 2. So what do I get? I get 3 times 2, because this is 2, and this is 2 right here, right? It says the integral of f of x is 2. So these are the same thing. Okay, so now what about g of x? Well, it says, remember, it says the integral g of x, that's just 10. This becomes a 10, and this became a 3 over here. Okay, so minus, well, it's just 10, right? So I get 3 times 2 minus 10, so I get 6 minus 10, and I get negative 4. So that's all there is for that one. And this one was really just a basic exercise to show you that essentially what's happening is that I'm basically just demonstrating some of the properties of integration. That's all. So now let's do some examples. Let's try this out. So I'm gonna clear the board right now. Yeah, we lost all of those. If you wanna go back and look at those properties, feel free to screenshot them and save them if you want. Memorize them, definitely. So there's this thing, called the fundamental theorem of calculus, and I don't really want to go too much into it, but the first part, it's a part that I don't really see used that much. Part one is basically this, and I'm just going to kind of do an example because I don't really want to go too much into the theory behind it. So let's say I had like g of u is equal to e to the x 1 ln of t dt. So if you're asked to solve something using the part one of the fundamental theorem of calculus, what it basically states is that the derivative of the integral, the derivative and the integral sign will essentially just cancel out. That's kind of the idea. But if I'm solving this, then what I want to do is if you're going to have like some x power as some x variable as one of your limits of integration, bring the x1 to the top. It always has to be on top. So 1 e to the x. So the one that involves x goes to the top. But remember, if I do that, if I switch the order, I got to add the negative. Okay? So ln t dt. And then what you do is you have to say u is equal to that x upper limit, whatever involves x. If this was just simply x squared, I'd say, hey, let u equal x squared. And then we take the derivative of this. So du over dx equals e to the x. Okay, so now what we do is we have to do this. We have to say, so what we're going to do is we're simply going to just take the derivative with respect to u of negative 1 e to the x ln t dt. And then all that happens here is that this will become a negative ln u, and then basically you just multiply it by du dx. And I should have read that du dx over there too. And then, well, what was u? Well, u was e to the x, and du over dx was e to the x. So the natural log of e to the x is just x, so I would get negative x times e to the x. And that's the answer. So again, I'm only going to do one of these because I don't really think this is all that useful, honestly. But the idea is that it's really just a procedure to remember. If you're given a limit of integration that's in terms of x, you always make sure that's at the top. If it's already at the bottom, then you bring it to the top, you add the negative out front. Then you let u equal your upper limit of integration. In this case, it's e to the x. You take the derivative of it. And you don't even have to worry about this. You don't even have to worry about this. All you would do then is then you plug u in for this function right here, ln of t. So I would just say, okay, negative natural log of u, well, u was e to the x, and then you multiply it by du over dx. So then u was e to the x, so negative natural log of e to the x times e to the x, and that evaluated to negative x e to the x. So that's all there really is for that. So now let's go into part two of the fundamental theorem of calculus, which is extremely important. So part two states this. It essentially states that if I have an integral from a to b running, so f(x) dx running from a to b, that will evaluate to, the antiderivative evaluated at b minus the antiderivative evaluated at a. Again, don't really worry about memorizing this because as you do these problems, it's really just going to become second nature just like that. It's like you don't memorize like certain formulas for other things in math anymore. Like, you just kind of do it. You don't remember like the procedure for addition and subtraction. You just kind of do it. Like you don't think of like a really procedure. It's kind of like that. So really what's happening is this is really the shortcut. No more Riemann sum stuff. This is a shortcut right here. So let's do a really basic example. Let's say I had -5 times 5 e with respect to x. Okay, so what's happening here is that e is just a constant. And remember what happens to constants in integrals or antiderivatives. If I had just 2, that would become a 2x, right? So that just becomes a 2x. If I have an e, that just becomes a ex. Wouldn't you agree? So this would become ex, and then you write this little bar. So you write this little bar right here, and it simply consists of your upper and lower limits of integration again, 5 to -5. Okay, so now what you do is then you plug in. So it's e times 5, where I'm plugging in this upper limit of integration in right here, okay? Minus, so it's always minus, so you plug in the first one, and then now we're working with this -5 over here, so minus e times -5, okay? So then I get, and let me show you where that came from too. That just came from by plugging this in. So, you evaluate it at the upper limit, you plug that into your antiderivative. The antiderivative of e was just ex. So I plug I plug my b value in, 5. Okay, and once that's plugged in, then I do a subtraction always, and then I plug -5a into the antiderivative, e dx, so I get minus e to -5, so I get 5e minus -5e, and that's just going to be 10e. Again, this is much shorter than the Riemann sum method, I believe. So, this is definitely something you want to memorize. Okay, so let's do another one. Okay, let's try this. So let's say I was given an integral. So the integral from 0 to pi over 2 cosine x with respect to x. Okay, so let's just take the integral of this. That's all we have to do. That's really all we're doing. We're just taking the antiderivative of this. Well, the antiderivative of cosine, well, what's the antiderivative of cosine? That's just sine. And then we put that bar. So we're going to put that bar right there. And it's running from this to, so running from 0 to pi over 2. It's simply our upper and lower limits of integration. Then you just do sine of pi over 2. This gets plugged into that. The upper limit of integration gets plugged in. Minus, and then we plug in the lower limit of integration. Okay? So again, pi over 2 gets plugged in for x here, sine of pi over 2, and then we do minus sign always. And then we plug in a 0 minus sine of 0. So sine of pi over 2 is simply just 1, sine of 0 is just 0, and I'm going to get 1 as my answer. So let's do one final example on this. And again, this is pretty easy. This isn't too bad. This is much better than the Riemann sums I was doing in the last video. And yeah, I know I keep complaining about that. It's just a terrible section, honestly. Okay, so -1 to 2. Okay, so 3. So 3x minus 2 x plus 1 dx. So remember what I said about integrals. They really can only be split apart between addition and subtraction. I cannot just do 3x minus 2 times the integral of x plus 1. That's really bad. Don't do that. You'll get the wrong answer, definitely. So what I have to do here is I have to make some sort of algebraic manipulation. That's usually the case for integrals. You always have to make an algebraic, you have to manipulate it algebraically to get it in terms of addition and subtraction, because we cannot just do, um, there is no product rule here. So what I'm going to do is FOIL, and that's usually the case for basically just for factors like this. So if I FOIL this, this is going to become 3x squared, right, plus x minus 2 dx. So now I'm just going to take the integral of this. So remember, you add 1 to the numerator, that becomes 3, and you divide by it. It's going to be x cubed plus 1/2 x squared minus 2x, and then you draw the bar from 2 to -1. And then now, you first plug in your upper limit of integration. So we're going to plug that in. So I get 2 cubed plus 1/2 2 squared minus 2 times 2. Okay, and then a minus sign, because we're done with our upper limit of integration. We do the minus sign, and now we plug in the lower limit of integration. So -1 cubed plus 1/2 times -1 squared minus 2 times -1. And again, I'm just plugging all of this into here, into this function. Okay, so if I do this, I get so 2 cubed, that become 8 plus 1/2 times 2 squared, so 1/2 times 4, so then minus 4, and then basically here. So what would this leave me with? So 8 plus 1/2 times 4, that's simply 8 plus 2 minus 4. So 8 plus 2 minus 4, I'm going to get 6. So over here is just a 6, and then I still have to do this one. -1 cubed is just -1. 1/2 times -1 squared, that's just 1/2. And then minus 2 times -1. Well, 2 times -1 is just -2, and then I subtract that, so that's just going to become a plus 2. So, okay, so basically just 2 minus a 1, that's just 1, plus 1/2, that's just going to give me 3/2. So I get 6 minus 3/2. And my answer then is just going to be 9/2. And that's my answer for that one. Pretty basic stuff, really not too many steps. Again, you take the antiderivative like we did a couple videos ago. Then you just have some values to plug in. You plug in the upper limit of integration first, you subtract, and then you plug in the lower limit. And then you take those numbers, you subtract them, you do the basic arithmetic, and you get some final answer. And in the next video, I'll be going more into integrals, and I'll do a lot more examples. So as always, thanks for watching.